for my other classes, my other class. And what I want you to do is tell me which problems from Progress Check C you'd like me to do. Which problems from Progress Check C do you want me to cover for you? Now, admittedly, I look here and I go, there's only 48% of you that did Progress Check C. So that's a problem in and itself, but I would be happy to go over any question you have.
8 through 12.
8 through 12, okay. I will do 8 through 12. Any other ones? All right. One second, let me open that up. I gotta get the chat. You were supposed to know the stuff from Progress Check C. I think there's a couple that maybe are on there. Jonah, don't just ask all the ones that JC didn't ask. I mean, I can go look here and we can put you out and see if you even did it. But don't, and that means,
did.
Huh?
I actually did, but I set a timer for 5 minutes.
5 minutes to do 18 problems?
No, 12
That's foolish.
problems.
That's foolish, but okay.
12 problems.
Okay. So, I mean, I'm happy to do as many as you need me to do, but if you didn't spend the time doing them, then, you know, A, shame on you.
I'm just kidding. I spent time on it.
Okay. Then B, you should make sure you do that. So I will, I'll go through as many as I can, and I'm not sure I'm going to be able to get through all of them, but I'll do my best. So take this one. This is question number 1, and you're given this graph. It's the graph of F, not F prime. And it says, which of the following could be the graph of F double prime? Well, so notice that if, when you think about what's happening, this graph looks like it's concave down, and it looks like somewhere right around here, this graph shifts to concave up. If you think about what that looks like. So if we have a graph that kind of goes like this, and then it looks like it goes like this, somewhere right here, there is a shift from concave down to concave up, and this is the graph of F. What that means is F double prime needs to go from negative values to positive values at that same X value. So whatever this is, X equals C, whatever that value is, that's what needs to happen here. The second derivative needs to go from negative to positive. So if you kind of scroll down and you start looking at some of those values, and you look at which one would match up, hopefully you see that that's the only one that does it. It's the only one that goes from negative to positive at that value. This one goes from positive to negative. This one doesn't change signs. Neither does this one really. We don't know if it really changes signs there. So the only one that makes sense is this one right here, and it comes from this idea over here, and this is really just the chart, right? It's just an adaptation of the chart. And so that's how you would do question number 1. Question number 2. You get these graphs labeled 1, 2, and 3 are shown. One is the graph of F, one is the graph of F prime, one is the graph of F double prime. That's something that we did in on delta math. Pretty similar, identifying F, F prime, F double prime. We have to kind of think about where things are. It'd be really nice if they were lined up, one on top of the other, but I don't know that I can do that. I wonder if I could take pictures of them and then superimpose them. I suppose I could do that. So what I'm going to do is I'm going to kind of look at what you have for each one. Notice that at this value 2, we have a jump on all of those. So I don't know that that's really going to help too much. When you think about the chart and you think about going from F to F prime to F double prime, and you think about what that looks like, you should have this kind of memorized on some level, where if you got increasing positive, decreasing negative, concave up, increasing positive, concave down, decreasing negative. So we should have those ideas here. So notice at 1, 2, 3, this graph changes from negative to positive. So if one of these was a derivative, or if this was the second derivative, one of these graphs at 1, 2, 3 would need to be changing from decreasing to increasing. Because if you're going from negative to positive, you're going from decreasing to increasing no matter what. And I don't really see that happening on any of these. So this one's not going to, so that might give you some clue into what that one is. So let me just pull off where. So right away, if that's true, and I'm going to see if I can annotate this, is this one's got to be F, because otherwise you'd see something significant happening in one of these where this would represent some sort of relative minimum. Now, if this is F, notice that this graph at somewhere around this value, we're going from increasing to decreasing right there, which means we need a graph to go from positive values to negative values at that same value, 1, 2, 3, 4-ish. So 1, 2, 3, 4. Well, it doesn't happen with that one, but it does happen with this one. It goes from positive to negative, which means this must be F prime. And then notice that right here, this graph goes from increasing to decreasing. And notice that that right there, we're going from positive to negative. So that would be F double prime. Okay. Any questions on that? All right, I'm going to clear those annotations and then go on to question 3. Okay, so here's a graph of F. So it's really important to know what you're looking at. Which of the following could be the graph of F prime? Okay, so again, we're kind of saying, okay, this is what we're given, and we're asked about F prime. So if that's true, I'm going to annotate this again. I'll do my best to kind of, but notice right here, we're going from increasing to decreasing. Then right here, we're going from decreasing to increasing. And then right here, we're going from increasing to decreasing. If that's what's happening with F, then what would make sense is f prime would need to be going from positive to negative to positive to negative at those same values, roughly. Does that make sense? Anybody have any questions on that? So we need a graph that goes from positive to negative to positive, and that one doesn't do it. Now that one's going from negative to positive. So this one's going from positive to negative to positive to negative. So that's could be it. It's really hard with my annotations on here and not seeing the whole thing on there. Clearly this is not it, because that doesn't change signs enough. We really need a sign change once, twice, 3 times. And so once, twice, 3 times, that happens. So when you match it up, this one doesn't have enough going on compared to all of the stuff that's going on in this one. That's the best I can maybe say on that, on how, and without looking at, and there's a they do more of an explanation on it. When you click on the answer, they'll go into more explanation on it, but it's hard to do it with only a small screen to show you. Okay, but it's all coming from this chart. Okay, so 4. The acceleration in meters per second is given by this. What is the car's maximum acceleration? So if you're looking for the maximum acceleration, you're trying to maximize this. Now, you don't have to really think, oh, isn't that another step up? You have to just know that if you're going to try to find, and this doesn't say find the absolute maximum or the relative maximum, it's saying find the maximum. Meaning if you have a function and you're trying to find the absolute maximum or minimum, first thing you do is find the critical numbers. And then we make a table and calculate the y values. And then answer the question. So that's how you find an absolute minimum or maximum. This particular one is saying, okay, here is the acceleration. What's the maximum acceleration? So this is this is what we're doing. We're going to do this with this function a of t. It really doesn't matter. They could have named this f. They could have named it j. They could have named it anything they wanted to. But you know that you're trying to maximize this function. Trying to highlight it. We're trying to maximize that function. So here's what we're going to do.
Don't you have to take the derivative?
Yep. So we have to take the derivative of this function, which is 3t squared minus 15t plus 12, right? We have to take that and we have to figure out when is that thing equal to 0, because again, we're trying to find the critical numbers. We're doing step 1 here. That's what we're doing right here. We're doing step 1. Well, if I factor out a 3, I'd have that. So if I continue to factor this, you got t minus 4, t minus 1 equals 0. So t is equal to 4, or t is equal to 1. So there's our 2 critical numbers. Now, what we're doing on this is we're going to go back here. I'm trying to get that not highlighted. There we go. Is the next step we're going to do is we're going to make a table. And the table we're going to make is going to have x and really a of t, because that's the function that we're maximizing. We're going to start our table at 0. We're going to end our table at 6. And we're going to put our critical numbers in that table as well. And now what we're going to do is we're going to go through and we're going to plug in those values into here. And remember, we're trying to figure out what the maximum is, okay? Any questions on that? Now, right away, you should know that B is not the right answer because T equals 28 is way outside of our T values here, right? So we're gonna try to maximize this. So what we're gonna do is we're gonna say, well, A of 0 is really equal to 10. Or does that make sense that that one's 10 if I just put 0 in here, here, and here? Hopefully that makes sense. That's not even one of the answers. Technically, maybe you didn't even need to test that because it's not even one of my choices. You know, it only asks me to check 4, 1, and 6 because I know 28 is way outside of my boundaries here. Okay, so if I put in 1, that'd be 1 cubed minus 15 divided by 2 times 1 squared plus 12 times 1 plus 10. You know, if I kind of keep on thinking about what that is, that's 1 minus 7.5 plus 12 plus 10. Okay. Any questions on that? I'm going to do that same thing for 4. Okay, I'm going to do that same thing for 4. So we're going to do 4 cubed minus 15 divided by 2 times 4 squared plus 12 times 4 plus 10. And then I would do it for 6. And then I'm just going to calculate it and pick the maximum one. Without going through and calculating it, we'll see what that, so it's this one down here if I calculate it. Okay, and that's all they're doing down here. They're just going through and calculating them. Any questions on that? Okay. 5, although we could do it, we're gonna hold off on 5 because it's a part that we didn't really we're not gonna do 5 because it's a maximization, it's called an optimization problem, and we're not gonna do that one. And just because I think there's a couple in here that we're not gonna do because we didn't really cover those. We kind of did, but we're not really gonna go through that 5. And I think there's another one in here. I know we're not gonna do 6. Same thing with 6, because we may cover that later on in the year when we start to review for the AP exam, but it's some things that we didn't cover. So let's go to 7. So don't worry about 5 and 6. So 7, at what value does the curve have a horizontal tangent? Well, what do you know about horizontal tangents? What do you know about horizontal lines?
The derivative is 0.
That's right. Super, Luke. Good to see you, Luke. Well, not see you, but see your name. We know that f prime is equal to 0, or the slope is equal to 0, right? So that's what we got to figure out. We got to take the derivative of this. Now you might go, oh my God, I can't take the derivative of that. Well, that's going to give you some some practice at if this is the function, and we have to differentiate that function. This is 2x. The derivative of e to the xy is e to the x minus y times, now we have to differentiate x minus y, 1 minus y prime. And now I have to solve for y prime. Do you remember doing that? You should. I mean, that's what we did first semester. So if I solve for this, you got 2x is equal to e to the x minus y minus e to the x minus y times y prime. If I continue to solve for this, so I have that. So I'm trying to figure out when is this thing equal to 0. So I'm trying to figure out when is 2x minus e to the x minus y equal to 0. Let me just make sure that so that when they go through the answer key on this, that's what they're doing on this as well. See if I want to do any more on this. I don't know if I want to do any more on this. Calculating that, you maybe could say, okay, well, let's just plug in these values. You know, this is a multiple choice, right? So we need this to be true. What value of x does this curve have a horizontal tangent? Well, if we pick 1 in here, we could figure out what y is. If we put square root of 2 in here, we could figure out y is. Put 2 in there, we could figure out what y is, and then we could take those points and plug them in. So at this point, I would do a little trial and error on this one, honestly. If I were doing this, is I wouldn't necessarily go through and try to figure out what x and y is here, but I would pick these values and then figure out what y would have to be and see if that y value works in the original equation. Okay, that's a pretty tough question, I think, on that one. Same kind of thing on this, and we're using implicit differentiation again. So if you're like, oh my God, I can't remember how to differentiate that, then let's do that first. You got x cubed plus y cubed minus 12x plus 16y equals 28. Again, which of the following statements we're looking at? Horizontal tangents, vertical tangents. Horizontal tangents is when the derivative equals 0. Vertical tangents is when the denominator of the derivative equals 0. And then tangent to the curve has a slope of 1/2. Well, we got to figure out what the derivative of this is. So just to give you some practice at doing that, if we differentiate this, this would be 3x squared plus 2y times y prime minus 12 plus 16 times y prime equals 0. And that's that implicit differentiation that we did a long time ago. Some of you did it when you were in Johnson's class. Some of you did it in my class. If I keep on solving this, I might have something like this. Okay. If I factor out a y prime, then I would have 2y minus 16 down here. If I go through this, I can then go, okay, in order to have a vertical tangent, 2y minus 16 has to equal 0. So y has to equal 8, negative 8, right? Did I do that right? Wait, this is plus here. This is plus. So that's 1. So that covers Roman numeral number 2. I need 12 minus 3x squared to equal 0 for a horizontal tangent, because I need the top equal to 0. So I need 3x squared to equal 12. So I need x squared to equal 4. So I need x to be 2 or negative 2. That covers Roman numeral number 1. And so this is Roman numeral number 2. This is Roman numeral number 1. So Roman numeral number 3, I just need to figure out if I have the point negative 1, 1, do I get 1/2 when I plug it into this derivative? Y prime is equal to 12 minus 3 times negative 1 squared over 2 times 1 plus 16. And if you calculate that, you will get, you'll get 1/2. You get 9 over 18, which is equal to 1/2. So that's Roman numeral number 3. That's why the answer is D down here. Any questions on that?
Wouldn't number 2 actually be 8, because isn't it 2y minus 16?
No, up here, if I differentiate 16, if I differentiate
2y plus 16.
It's 2y plus 16 up here. Yeah, I think I wrote negative when I forgot, and I didn't write that as negative, or I didn't write that as positive the first time, but it's 2y plus 16. So that's the one that I'm going here.
Okay.
All right. I got to look at the time. Okay, so I think we'll have enough time. So in the XY plane, how many horizontal or vertical tangent lines does this curve have? Again, we're doing the same kind of thing on this. We're finding the derivative. So this is some practice on some stuff that you did previously. So if you're kind of going, well, I don't remember how to take the derivative of x times y squared is equal to 2 plus x times y. That's what we're doing this. That's why you got to go back and look at this. We still have to know how to take the derivative of these. We're going to have to use the product rule because there's a multiplication here and there's multiplication here. So if I differentiate the left side, I would have 1 times y squared plus x times 2y times y prime. If I differentiate the right side, I would have 1 times y plus x times y prime. Any questions on that? Okay, so to keep on going with this, now I would have to get all the y prime stuff on one side. So I'll just get it on this side. So there, I moved this y squared over to this side. That's why it's negative now. I moved this x times y prime over to the other side. That's why it's negative now. If I factor out a y prime, I have y minus y squared divided by all this other stuff. And I have that. Okay. Now, if I'm calculating the horizontal and vertical tangents, I'm trying to figure out when the numerator is equal to 0 and when the denominator is equal to 0. Okay, so I might say, you know, for a horizontal tangent, I need to figure out when y minus y squared is equal to 0. I factor that. That's when y is equal to 0 and when y is equal to 1. But you really kind of got to go back up here and plug it in. So notice that when y is equal to 0, from the original equation, that'd be x times 0 squared equals 2 plus x times 0. Notice that that means 0 equals 2. So that's kind of a false answer. So we know there's one vertical tangent or horizontal tangent right here, but not two. And then we do the same thing, finding the vertical tangent where, you know, this is when this equals 0, we have a horizontal tangent. When this equals 0, we have a vertical tangent. So that's how we're going to calculate those. And that's what they do when you look at their answer on here. One vertical, but no horizontal. So I guess if I plug in 1 up here, I probably run into some situations on here that doesn't work out as well. Okay. Pretty tough question on that one. So all in all, this progress check is much harder than the other ones. Well, the last back half of this one is. I'm looking at the chat to see if there's any questions, but I don't see any. So, you know, again, here we're looking at derivatives, right? We're trying to figure out when something's concave, which justification is for the concavity. We need to find the second derivative. So just to show you how to do that second derivative on this, if you've forgotten, the first derivative is 2x plus 2y times y prime equals 0. So y prime is equal to negative 2x over 2y, or negative x over y. You remember that? So then the second derivative, because we're talking about concavity, so we're going to have to find the second derivative. We're going to have to use the quotient rule on this. So the low times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So now if I keep on going on this, I got negative y plus x times, notice this is negative x over y, because that's what, if you remember, that's what y prime is. So we can put that in there, divided by y squared. And then they're going to do some simplification on this to calculate this and get it in terms of x or y. Do you want me to simplify that? Do you want me to show you the algebra to simplify that or no? Don't be afraid, but I'm not going to do it if you don't need me to. All right, I'll take your silence as no, you don't need to simplify it for us, Alquist. They go through and simplify it right there for you. Okay. So you go through and simplify it. So lots of implicit differentiation on this one. Same thing with this one. Maybe doing 11 and 12, or 11 for sure, is something that you should try again now that you've seen me do several implicit differentiation problems that you haven't done for a long time, admittedly. So this one is kind of coming back. So especially those of you who were on unit 2, and that implicit differentiation was specifically, I'll tell you where it was. It was actually section 3.2. So if you remember section 3.2, that's where that implicit differentiation was. And same thing with this one. So lots of implicit differentiation on this. So go back and look at doing implicit differentiation on 11 and 12 and seeing if you can come up with the value on these. I can do them if you want me to, but I just don't want to do them if you just forgot how to do implicit differentiation and now you've seen me do them again. If you still want me to do 11 and 12, tell me and I'll do 11 and 12 right now.
Wait, can you simplify this?
This one? Yeah. So if I were going to simplify this, I'm just going to work with the left side, okay? Or in the right side. I'm not going to work with the left side because we know the left side is the second derivative. So I have this, right? Does that make sense? Stop me. Actually, just stop me if you say I don't understand what you did there. Stop me. So then this is okay, if I multiply by a common, if I multiply this by y over y to get that to be equal, does that make sense? Hopefully that makes sense. So then this is negative x squared plus y squared over y times 1 over y squared, right? Let me go back to the equation so you remember what that equation was, okay? So this is negative 36 over y cubed because x squared plus y squared equals 36. So, I mean, that's a pretty tough simplification on that, right? I mean, that's pretty nasty simplifying on that, but that's what it is. I'll scroll. So it's, backing it up is once you found that second derivative, it came down to simplifying it. And this was and it says y is greater than 0. So since y is greater than 0, this quantity is less than 0, which means the function is concave down. And it actually is the only one that turns out to be negative 36 over. So you wouldn't even need to really know that other than simplifying it gets you to that. Pretty nasty simplifying, but it's, I mean, I guess it's not undoable, but it's not the easiest thing. Okay. So if you were kind of struggling on this with the implicit differentiation, I get that. I mean, I understand why you'd struggle with that. Hopefully it's not brand new and you're going, I've never seen this before. Hopefully you're going, I just forgot how to do implicit differentiation. And if that's the case, fine. But that's what will happen. You'll have to go back and look at some of these things. So this is applying something we did way back in section 3.2 to something that we're doing in section in unit 5. Any questions? And it's not lost on me that this is much harder to do distance learning wise and not getting help on it as much as you maybe normally would in a class. All right. In power, in this, I'm going to show you. Today's lesson, we kind of have completed unit 5. And so now we're working on, we're beginning unit 6, which is called doing anti-differentiation. So the opposite of differentiation. So think of all of the rules that we learned to do derivatives, only doing them in reverse is all we're doing. And the assignment for today is a Desmos activity. I think it's a pretty good one to walk you through how to do at least the initial step of this. So it's really going to be important for you to do this activity. I don't think it'll take terribly long to do it. You got today and then tomorrow to do it. Remember though, when you do a Desmos activity, if you click down here, it won't go anywhere. You actually have to click this up there. That is the link. Once you click that link, it'll take you to the activity. Okay, so it'll pull you to the activity. So if you don't click that link up here, you won't get a new window. If you try to do it down here, it'll just say you're having an error signing in. Okay, so you need to, by Thursday, to be on track, you need to do that activity and do this this FRQ. Remember to report your thing. I put the answer key in, I put a video solution to that one already on there. Okay. Any questions? Okay. And you really want to do this first thing to get to, otherwise Thursday will be kind of a nightmare for you. But this one is not very threatening. This one is actually pretty nice. It walks you through some nice things, so, okay. Okay. If you need more, stay on. Actually, you can't, well, you got to go to 7th hour is what you got to do.
Thank you, Mr. Alquist.
Thanks, guys.
Thank you.
Thank you.
See ya.